So hello everyone. So today's problem is dice through. You have given n dice with m faces. Find the number of ways to get some x, which is the summation of values on each face when all dice are thrown. So let's see test cases to better understand the question. So m is given as 6. So the value of faces can be in the range of 1 to 6, including 1 and 6. And n is 3, which means we have 3 dices and we have to have a target of 12. So let's see for this a quick example for this particular test is, can we take one? So this is the dash number one, dash number two, dash number three. So can we take one here? Yes, we can. It's a valid phase. Can we take two here? Yes, it's a valid phase. We can. We can take three here. Yes, but the summation is six. We need summation 12, not six. So can we change these values to bring 12? That is the point of the problem. We have to change this combination, this pattern we have to change so that we get 12. So can we take 4 here, 4 and 4? Yes, we can take. We will get 12. Can we take 1, 5, 6? Yes. So 4, 4, 4 was one combination. 1, 5, 6 is one another combination. So we have to add all these combinations. So 1, 2. So totally there are 25 combinations as stated in the question. So let's see the problem number, test case number 2. We have given m is equal to 2 and n is equal to 3. So 1, 2, 3, 3 addresses we have given and m is 2. We have to find the value of 2. So we can take 1 here, we can take 1 here, we can take 2 here. But will we get 6? No, we are getting 4. So can we change this to 1? No. Can we change this to 2? Yes, we can. And can we take 1 here? Yes, we can, but it will give you 4. Can we take 2 here? Yes, we can, but it will give you 5. So we have to change this to 2, this to 2, this to 2. So this is the only combination that will reach you and give you 6. So 1 is the output. So let's see the recursion tree. It's a very simple DP question. Let's see the recursion tree for the same. So firstly, we'll take m as 2, n as 3, x as 6. So initially the state is, this is the second example I've taken because the first one is very large, so I'll not be able to make the recursion tree for that. This is simple. I can easily make the complete recursion tree for the same. So firstly, for the first dice, which is the dice number 3, for dice number 3, we have two choices because m is 2, so it could be in the range of 1 to 2. So in the first one, I've taken the choice as 1. For the second one, I've taken the choice as 2. So if you get to this state, the x values was initially 6. After reducing 1 because we have taken 1, we'll get 5. So in this state we have taken 2, so it will reduce to 4. So for this particular case as well, n is here, n is 1. Okay, n is 3. So we have two more dices because we have used one dice. We have two more dices. So for this particular, for dice number 2, we have two choices as well, 1 and 2 because m is 2. If you take 1, n will come as to be 1, x will be 4 because we have taken 1. If you take 2, it will come as 3. And for this particular dice, for n is equal to 1, which is for the dice number 1, we have two choices. This will give you x3, x is 2. So we want x is equal to 0, but we are getting x is equal to 3 and 2. So we don't have any valid combination, so we'll return 0. Same here, we'll return 0. We'll add all the combinations, all the possibilities. So 0 plus 0 is 0. So we'll return 0 from here. So let's see this. We'll take 2, it will give you 3. So for n is equal to 1, you have 2, m is equal to 2, and x is equal to 3. So you'll not be able to get 3. So we'll directly return 0. You will return 0. And you'll add all the combinations. 0 plus 0 is 0. So we'll return 0. And this will also add all the combinations, and it will return 0. So we have completed the left subtree. Let's see the right subtree. For the dice number 3, you have taken 2. So it will bring you to n is equal to 2 and x is equal to 4. So you have two choices. You can take one or you can take two. If you take two, you'll get, you have one dice. We have used two dice. You have one dice left. You can take two further and you'll get x is equal to 0. For every other combination, you'll get no valid combination. So you'll return 0 for all of them. This will also return 0. This will return 1 because we have a valid combination x is equal to 0. So we'll return 1 here. We'll add all the combination for this state. So 0 plus 1 is 1. So this will return 1. 0 plus 1 is 1. So this will return 1. And this, for the left subtree, it got 0. For the right subtree, it got 1. So it will add all the possibility and return 1. And that indeed is our correct answer. So let's see the code. So let's see the recursion code. So recursion code, as we have seen, m, n, and x is required. N and x is changing. If you closely see, n is changing from 2 to 1, x is changing from 5 to 2. M is not changing. So if we read, if we reach n is equal to 0, in this particular case, if you reach n is equal to 0, we don't have any more dice. So we'll directly check if x is equal to 0. If it's not equal to 0, then we'll return 0 because it is not a valid combination. And if we reach 0, we will return 1 because it's a valid combination. So that is what I've written here. And for I in the range of 1 to m, because we have to check every possibility from 1 to m. And we have to add all the answers that we get from the states. So for this particular state, it's left subtree is returning 0, right subtree is returning 1. So we have to return the summation of all, which is 0 plus 1 is 1. So that is the complete code. So time complexity is m power n because so for every state there could be m possibilities. So, and they are total n dices. So m power n is the time complexity, and the space complexity is also the same because that is the auxiliary stack space. This much stack space is required. So it's an exponential time complexity as well as space complexity, which is extremely inefficient. So for this, we can apply DP or memoization. So the DP and memoization code is very similar to the recursion. Just we add a DP. As you can see, n and x is changing, so we need two states to determine the result, which is n and x. So n plus 1 because we can take n is equal to 3, n is equal to 3 and x is equal to 6 also is also a state. So we have to take a DP array for n plus 1 and x plus 1. Everything remains the same. If we have already seen the DP and we have already computed it, we'll directly return it. Otherwise, we'll store it. So hope you like the explanation and hope you understand the question as well as the solution. Thank you for watching.